Afternoon everyone, it's Deb Sparks from the Centre of Excellence for Prescribed Burning here. Welcome to our webinar today. I'm really pleased to be able to present Dr Tom Remenyi from the Antarctic Climate and Ecosystems CRC, and he's going to talk about some research that they've been doing into how climate change scenarios may impact on prescribed burning. So on that note, I'll hand over to you, Tom.
Thanks very much, Deb. Is that working as far as you can tell, Deb?
Yes.
Okay, great. So, g'day everybody. Thanks for attending the webinar. I'm working on this in collaboration with my colleagues Rebecca Harris, Paul Fox-Hughes, Peter Love and Nathan Bindoff, and we're part of the Climate Futures team here at the ACRC, all part of the University of Tasmania. This work has been done for Tasmania, and it's going to be more of a indicative of what will be happening across the rest of Australia, although we haven't done the work in that space. So this project started, our work in this space started when Paul Fox-Hughes was investigating climate change impacts on forest fire danger index into the future. He found that there was going to be a steady increase in fire danger into the future, particularly in spring, which meant longer seasons with a much earlier start date and a bit later finish. It basically resulted in double the danger over twice the area, so the intensity and the area needed to be covered was going to increase, and this made Tas Fire and the other fire managers in Tasmania realise that given the limited resources they had to really start thinking about the strategies they were using now and whether they were going to work into the future. So in the figure you can see here that there's this like cigarette burn that comes up in the sort of Central Highlands region of Tasmania. Forest fire danger, that index is not particularly useful for a large portion of the state, which is not mostly the southwest where the Tasmania World Heritage Area is, but it does give a very strong indication of some of the increases in forest fire danger or in danger of fire in those regions moving forward. So this is a statewide assessment. In this particular study, and we're taking that further this year, but in this particular study we investigated all of the variables independently, and that's actually turned out to be really, really useful for the departments because they use different indices for different things, and this particular study has allowed them to use that inside their decision-making processes outside of prescribed burning. We investigated temperature, rainfall, relative humidity, the soil dryness index, which does happen to work quite well down in Tasmania for some areas, much better than the KBDI, which some of you may be familiar with. We also used drought factor, the forest danger indices of Forest Fire Danger Index and the Moorland Fire Danger Index, which is important for that region number 9 that you might be able to see on the slides there. I'll just see if I can get my pointer up. This one here. C. Haynes, which is an indication of atmospheric stability that is important for fire, which many of you may be more familiar with using than what I am. Wind speed and direction were also used, and we investigated these changes to the seasonal values in current and the future time periods, which moved forward by 20-year increments, as you can see in that list there. Changes to the monthly values and the current future time periods is what I'm going to be presenting throughout this talk. We also did the assessment based on Bureau of Meteorology weather forecast districts. We chose that breakdown because the Bureau of Meteorology has kind of decided that the weather forecasts for those regions kind of make sense. So they're kind of discrete atmospheric units, and therefore they kind of made sense for us to break down our assessment of Tasmania into those units as well. So conditions suitable for prescribed burning are less frequent into the future, and that's what we found out of this study. I'll go into the details of it a bit later. This is driven because temperature is expected to increase, which everybody's pretty familiar with, I think, from at the moment. Rainfall is actually expected to stay steady, which was a bit surprising, really. Maybe there's a slight decrease, but certainly not enough to really kind of be worried about in the fire context. But it's the dryness that is expected to increase significantly, because as the temperature increases, the evaporative effect increases, and since rainfall is steady, then we end up with a drier landscape. So this increases the risks when burning. The consequence is that if we're going to have drier conditions more often, then the mitigation of using prescribed burning, you decrease the amount of time that you have to actually do that safely. And mostly the problem is that because of the very narrow window, which I'm sure many of you are more operationally familiar with than I am, that narrow window of when it's safe to burn in particular forest types or fuel types just decreases that frequency, and that makes it really hard. In the Tasmanian context, although we might be able to burn over winter, we actually don't have as much light, so your operational days and logistics actually decreases your capacity to extend into those periods. So just to give you a bit of a background as to how we use these variables or where they come from, we use a model called a conformal cubic atmospheric model. It's developed by CSIRO. It's fully dynamic, four-dimensional simulation of the climate system. And you can see a little bit of how that's moving here, where there are clouds moving at different layers in the atmosphere. We also have 6 layers in the soils to allow surface soils to dry out faster than the deeper soils. All at the moment, this in a graphic is showing surface temperature over Tasmania. You can see how as the clouds come over, it actually influences that surface temperature. We're watching it change hourly over a 14-day period here. And so we've got a lot of confidence that the climate that is represented in the simulation has a lot of similarity to the climate that actually happens in Tassie. And we also have data for this over Southeast Australia, ranging from west of Adelaide all the way up to the Gold Coast down to the southern tip of Tasmania. So we do have data to be able to extend this kind of work to other places in Australia. This project focused on the data set that we have focuses on trying to capture the resolution over the Australian Alpine region. And so we've got a 5-kilometre resolution there, and then 10 kilometres sort of as you move towards the edge of the grid. And so yeah, that's the underlying data. So let's have a look at what's going to happen into the future. So let's start with monthly temperature. The blue boxes are what we consider historical. The green boxes are what we're kind of on the cusp of moving into now, from the 2020 to 2040 for those that might not be able to read that. And the orange boxes are for the far future, which is 2080 to 2100. In temperature, we can see basically just a shift of the entire spectrum up by about sort of 3 to 6 degrees, depending on exactly where you are. And that's going to have a pretty big impact on some of these extreme events and extremes that we see. It's not as well represented here, but what this does show is that we're going to see extreme temperatures more often. And crucially, when we go down to, say, the winter periods, we're just not going to see, they're basically really cold periods start to become extinct. That has implications for a lot of the snow areas across Tasmania, and that changes the seasonal moisture balance as the snow doesn't hang around as long and impacts on say, regeneration of deep soil moisture, which can be important for those regions. This is almost exactly the same when we look at the minimum daily temperature, which I have just moved to, which you can see the difference here. These plots look so similar, and it's simply because in this kind of average context, it's just a shifting of the entire distribution up into a warmer section, as you can see here, by about 3 degrees into the near future. So that's sort of, I guess, relatively easy to understand and to see how that's changing. What was more of a surprise is when you look at these temperature changes in a seasonal basis. So let's talk through what this plot actually is saying. And there's a lot of information that's hidden in these few data points. So let's start with this section down here. Here is what the annual climate is going to be, in that historical period of 1960 to 1980. Spring is slightly cooler than the annual mean. Summer is a lot hotter than the annual mean. Autumn is slightly warmer than the annual mean. And winter is a lot cooler than the annual mean. So that's what this plot is trying to represent, is that difference through the season compared to sort of what's considered normal conditions. As we move into the future time period of 2020 to 2040, the annual climate warms up slightly, and spring, instead of being cooler than the current mean conditions, is starting to look a little bit more like autumn. Autumn's warming up a bit too. Summer is increasing at a larger rate than everything else, and at a larger rate than both spring and summer, spring and autumn, apologies. And winter is also warming up, but still quite cool relative to this current or historical annual mean. The dots on the side here represent the multi-model spread, and what this represents for us is that the models in temperature are all saying the same story, which gives us a lot of confidence that what we're expecting to see in temperature is something that we can probably expect to see in reality. And when we look at the historical record and what's happened over the last 20 years, the models have done an excellent job of representing that change. If anything, they're underestimating the rate of temperature increase. And so we're actually warming faster than what most of the models suggest, which is a little bit scary. But these dots here at each one of these steps just shows how tightly the models represent temperature, and that gives us a lot of confidence. Again, we're looking at minimum temperature now, and this is very, very similar story. A general increase into the future of mean conditions, and we're looking at, in this one, sort of 3 degrees into the future of mean conditions, 3 degrees warmer. And so this, very similar, not much additional to say in this sort of minimum temperature period. For the prescribed burning context, a lot of these minimum temperatures are important because that's what allows the fire to burn overnight, especially in Tasmania. And that was a really important part for them to understand about what does that mean, say, in spring or in autumn, where maybe the overnight temperatures are not getting down low enough to actually let the fire go out, or to, in fact, let the fire burn overnight is the key problem they have sort of at the moment. So they were very interested to see how this is changing. We've also got, as mentioned, monthly rainfall doesn't have that much of a change. If anything, we can see that in the winter periods there is a slight increase in rainfall over that period, but that is sort of offset by a decrease in the summer periods. The other periods are kind of a bit of a mixed bag. So we've got a decrease in the near future and an increase by the end of the century in October. The small changes are kind of expected, especially when you do monthly sums. The thing that is not represented here is that the period between rain events appears to increase. So there is an increase in the number of dry days. In a Tasmanian context, the kind of rule of thumb that they use operationally, I've been told, is after about 3 weeks, basically the entire of no rain, everything in the Tasmanian forests becomes burnable. So those increases in the length of time between rainfall events is important because it might increase the number of days when there is a risk. However, the overall sort of volume of rainfall that we're expecting to see is approximately the same as what we see currently, and that's made up because when it does rain, with a warmer atmosphere, it can carry more moisture in the air, and therefore it rains out. When it does rain out, the raindrops are bigger, the volume of rain that falls is larger. Now, when we look at how do the changes across the seasons compare to current conditions, we start to see a lot more spread in the model, across the models. The models sort of have less agreement as to exactly what they're going to see. In some cases, they don't even agree in the direction. So in autumn, for example, a couple of models suggest that it might get wetter, and whereas the majority of the models represent it's going to get slightly drier. This is something that we see a lot across the model spectrum, and it's something we try and portray throughout our information that we provide to stakeholders, because it's really important to know that there isn't one answer to this. We might have a situation where it's going to get wetter, and we might have a situation where it's going to get drier. Now, in Tasmania, the reason that we have this situation is because of the position of the subtropical ridge. A lot of Tasmania's rain comes from large synoptic systems coming across the Southern Ocean and smashing into the mountain, that is the whole of Tasmania, but poking out of the ocean. However, if those synoptic systems get pushed a little bit further south, then they don't even hit Tasmania at all, and therefore the rainfall doesn't fall over Tassie. So that's basic. So then, if it does hit Tasmania, then because the atmosphere is warmer, then the rainfall will be larger, and therefore we get an increase. However, if the broader synoptic systems push it further south, then we end up not getting any rainfall at all, and therefore we dry out. So that's the kind of the trade-off, and that's why at the moment that some of the rainfall information is quite spread. We understand what's driving that, and what we try and do is make sure that the stakeholders are aware of the, I guess, relative uncertainty in this space. And that's even more true for other areas, for other variables, apologies. This is just a little taster of how rainfall changes in all of the different regions. We can see some regions there are slight increases in the winter period. Other regions it's kind of flat and there's not that much change. And then in the summer period we have stronger decreases in some regions, especially in the southwest where the Tasmanian World Heritage Area is. But mostly these changes are kind of minor, and but there is variability across the state, which is why it's important to break down what's happening in different regions for an operational or a strategic point of view, to make sure there isn't a one-size-fits-all for the whole state. It's really addressed more in a nuanced way, and the operational decision makers have really appreciated having information that they can use in this context. So then we move on to drought factor. Drought factor, if you're not aware of it, is a index that's used by the Tasmanian fire managers to assess basically the availability of fuel on the ground. It incorporates soil dryness index, it incorporates which is antecedent rainfall and the like, temperature levels, evaporation rates. It kind of tries to capture all of that in a sort of longer term time frame. So if we have a very large rainfall event, that will have it'll take a lot longer for the drought factor to then return back up to higher or what's considered dangerous levels. What we can see here is that the historical period, which is this blue bar, is basically giving us a sense that the near future is going to look much the same. The spread, there might have, slightly, is very small differences between these two. However, by the end of century, there is definitely this shift as the temperature increases and the evaporation rates really start to kick in. Even if rainfall does increase into the future, that it does dry off a lot faster. So our January, February, March period is going to be a lot drier than what we've kind of been historically used to. Crucially, if you look at the spread of January here and you move over and look at April, then the April period can actually be quite dry sometimes in Tasmania, and that is going to increase slightly, so that this kind of extension of the January-like conditions from a dryness point of view really kind of starts to extend all the way through to about May, and then there's this sharp transition into the winter period. And this is what we've been seeing, and it's largely driven by this dryness component. Similarly, if you look at December, December has this similar kind of step change by the time you get to the end of the century, and it does mean that you're operating more like in January conditions in December. And similarly, in November, you're in more like December conditions. So it's kind of compressing the length of what's considered winter conditions and really kind of expanding what we would consider to be summer conditions. Similarly, this story, given it's driven largely by sort of the temperature rainfall interaction, and that rainfall isn't changing that substantially, this looks very similar to the temperature plots. We see a slight sort of, if we look at how what are our warm and our dry and our wet months. The wet months of spring really start to more look a little bit less wet, and that's where the extension of the fire season is really coming forward rather than sort of going back into autumn. But even so, autumn is now starting to look a lot like our current summer, and that's something that the fire agencies here are quite concerned about. So this is where we really get to see exactly what's driving all that sort of increased risk. It's this soil dryness index. The changes that we see in this are substantial. They do start to really kind of rear their head in the 2020 to 2040 period, but it's really that kind of rate of increase by the very end of the century, or the amount of increase that we're about to see by the end of the century is stark, especially if you look at these April-May periods. And so this is something that's of real concern, because these are the periods when a lot of the prescribed burning does happen. In this autumn period, it's not very windy, so it's a great time to be able to do a lot of burning down in Tassie. It has less other kind of cropping that interferes with that, that they have to work around at that time. And so the fact that this is starting to get up into potentially dangerous levels to start fighting fires based on the soil dryness is something that is a real concern, and they've been observing it in particularly warmer years, a decrease in the opportunities to implement their prescribed burning strategy. Interestingly, though, that the spring period is not driven by the soil dryness component. if you look at the changes that we're seeing here, they're far less substantial, and therefore the changes that we see in fire danger over this period are going to be driven more by windy conditions with the increased temperatures. When we look at this, again, these plots should be starting to look fairly familiar, although one of the things that is particularly stark on this one is how the models don't have very strong agreement in exactly the magnitude of change. Although the direction of change is usually the same, usually sort of agreed upon, the exception of winter down here, the spread is much larger than we see in some of the other variables. And this just goes to sort of reflect the uncertainty of these kinds of conditions once you start putting sort of rainfall into these calculations. Humidity is another important factor for prescribed burning, as I'm sure many of you are aware. And moving it into the future, it doesn't look like humidity is really going to change that much at all, relative humidity. And that's great to have at least one variable which we can have a bit more confidence around and know that we can work with existing conditions and existing policies. The Forest Fire Danger Index, which sort of underpins some of those danger ratings that decide whether it's considered reasonable to go out and start trying to do some prescribed burning, is, as shown at the very start, it's going to see some pretty major increases, especially in sort of the November through to March period. And I think we've kind of already covered that, so I'll skip forward. I'd prefer to be able to provide people with opportunity to have lots of questions, so I'll keep moving forward for that one. We have very similar looking plots here that they are driven by temperature change more than anything, and the feedback that has with moisture levels in the soil. This was so the Moreland Fire Danger Index is fundamentally different to the way that the Forest Fire Danger Index works. In a Moreland Fire Danger Index, you can actually have, it does not consider soil moisture at all, and the reason for that is because in some of these regions in southwest Tasmania, in the World Heritage Area, they are capable of burning even when they're in a puddle of water. So some of these plants are incredibly flammable, and therefore the calculation of any sort of fire danger in that region needs to be done a bit differently. Therefore the values that you're seeing there between 0 and 12 are kind of, it's relative to the Moreland Fire Danger Index and not relative to a Forest Fire Danger Index you might be used to seeing. The increases that we're seeing here are largely driven by changes in wind, and the windiness in sort of the August through to December period does basically increase, so that a lot of the risk of fire in these moorland periods is really inside the spring. Spring is the danger time for this period, but fortunately for any prescribed burning that does need to happen, the Moreland Fire Danger Index is suggesting that there's little to no change in the kind of autumn period, and that's actually quite hopeful, I guess, in this region, which is good because the vast majority of these regions are actually very isolated, and so those isolated regions need, prescribed burning is one of the few mechanisms that is going to work. And we can practically implement. So they look like those strategies might actually be okay for the time being, for some time in that period, although we're doing some more developed work on that with the Firescape model, which I can talk to later if anyone wishes to know more. Again, we're seeing a very similar story. It's really spring where we see this really large increase relative to the current conditions. Winter, there's also an increase in this kind of like risk. We're not sure whether it actually gets to a dangerous period at a dangerous values, but they certainly increase from something that's very, very low up to something that's quite high. It's approaching, sorry, it's a lot higher than what it was. And again, we can see this right here in this zone here, this kind of August through to November period, the winds really increase there in intensity. We are seeing a bit of that in sort of this July and August as well. However, because of the increase in rainfall in July, and that offsets some of those increases that we're worried about in that period. For prescribed burning, though, if we look at the typical period that the Tas Fire prefer to operate in, this sort of autumn period is actually, there's an expectation of increasing stability in the atmosphere, and this means this with much lower wind speeds, or more periods of lower wind speeds, which is quite encouraging. Although, as we've seen, it's not enough to then drop the conditions down to something that you would expect to be able to actually start off some of those prescribed burning strategies in that far future period. In the near future, though, that's actually increasing the windiness. Now, we're not sure how real this is, but you know, these kind of interdecadal changes that we see are real. They're a real thing. We certainly see them in the historical record, but in terms of are all the models representing that correctly is something that we probably have less confidence on, but it certainly is interesting to see that they all have such strong agreement in that space for wind, although I think that might be represented here in terms of what kind of agreement do they have. A lot of these wind in this middle period, which is where the models kind of disagree the most, the spread is enormous. Some are saying it will increase in speed, some will say it will decrease in speed. This is largely to do with this, again, positioning of these larger synoptic systems and where Tasmania sits relative to that. So that's what's creating this dichotomous relationship, I guess, between some of these models. It also could be because some of the models are in one phase and the other models are in another phase. And so, and that kind of can describe some of that uncertainty. Again, there hasn't been an enormous amount of work on testing wind to see how accurate it is represented and parameterized inside these models, and that's one of the things that we're moving forward on at the moment. So spatial variability of change in climate variables for the autumn period, which is the most important period for our stakeholders. The change that we're seeing in these figures here is relative to the baseline period of 1960 to 1980, and we're looking at the far future. So if we look at maximum minimum temperatures, we're looking at approximately 3 degrees over most of the state. In minimum temperatures, it's going to be, we're kind of, it's a rounding error when we really talk about what these changes look like. If it's 2.5 or 3.5, basically 3 degrees over the entire state with slightly higher increases at higher elevation. The more important ones that sort of, I guess, have stronger changes and more interesting changes, I guess, in some ways, is daily rainfall. And apologies for the size of the, if you can't read this, I'll explain that now, I guess. So this is the top two up here are temperature, maximum and minimum temperature. Then we have daily rainfall, maximum daily wind speed, drought factor, soil dryness index, forest fire danger index, and the moorland fire danger index. So just in case those labels weren't large enough. The regional variability that we see in fire danger across the state is driven all by this kind of moisture availability, daily rainfall here. And that kind of flows on through the drought factor and soil dryness, which is incorporated into some of these other fire danger indices at the bottom here. The dryness that we see is driven by this ridge line that goes down through Tasmania to the centre of Tasmania. The rainfall that we see on the west coast is somewhere in the order of sort of metres, and the rainfall that we see on the east coast is sort of more like, you know, half a metre. So, so in terms of total rainfall, there's a lot over the west coast, and so it kind of has more to lose in some ways, and that's why we see this very, very stark patterning of strong drying trends over the western coast, western half of Tasmania. But then on the eastern coast, there's a increased rainfall trend. This is because there's the east coast lows that are coming down sort of from Sydney, and they're making their way further and further south as the sea surface temperatures increase, providing those storms with more energy, and they can then travel further down the coast. They then come down, and they're called east coast lows for us down here. They come down and they spin around, and they really generate enormous amounts of rain up in this northeastern corner of Tassie. This northeastern corner can have some of the highest rainfall on a single day in the state, largely driven by those kind of systems that we see already. And the frequency of those systems is set to increase, is projected to increase, and that's why we're seeing an increased moisture level on this side, especially in this autumn, and there's also in summer periods. So the opportunity to do prescribed burning may increase on the west coast, but it also might become more dangerous and less capable, so might move through to the other end of the spectrum. And on the on the eastern coast, the increased moisture might mean that the opportunity to burn may decrease because we go down down so it's too low and nothing will burn. It'll be too wet to burn. So so the opportunities in almost all instances seem to be decreasing for prescribed burning, and this is a real challenge that we're working with the stakeholders to try and discuss what alternatives might be. So these implications, as the frequency of warmer and drier conditions increases in autumn and spring across Tasmania, this increases the likelihood that fires will either burn with faster rates of spread, higher intensities, and with a higher risk of escape than under current conditions. This is the dominant factor driving fewer opportunities to safely conduct prescribed burning. It becomes evident in the near future, but it will become unusable probably towards the end, which is what that substantial changes are expected means. More winter burning may be needed and may be possible. However, this has really difficult implications for Tasmania, where light, because of the shorter days over winter, that's not going to change. And so working in the dark, especially in remote areas, is really challenging. It will either require heaps more training, or it'll require many, many more resources to conduct the similar kinds of burns that you can do in the late autumn period. By improving the understanding of fire behaviour during prescribed burning, we might be able to more accurately identify when conditions are suitable. This might, by increasing that understanding, we might be able to increase the size of the windows, the number of windows that we might be able to choose. But we also could investigate different practices, like utilising finer scale weather forecasting, or doing mechanical removal of fuels, either by bulldozer or using animals, to maintain fire breaks. So these are some of the potential options that are being discussed. So temperatures follow gradual and predictable increases. They're consistent across the seasons. Other variables show strong spatial and seasonal variability, mostly driven by rainfall. these projections show a range of plausible futures, both wetter and drier, and spring and autumn increases in fire danger are projected with very large increases in the spring MFDI driven by higher wind, although the confidence on that is low. Projected changes to soil dryness, drought factor, may restrict opportunities for prescribed burning in the current preferable periods of spring and autumn. And this limited opportunity for prescribed burning in the future suggests the need to investigate these alternative strategies. And that's it. So if anyone would like to ask any questions, I'll maybe hand over to Deb to facilitate.
Thanks very much, Tom. That was really interesting to see all those graphs and the changes that are likely to occur. So just going to press a couple of buttons to open the lines up for people to ask questions.
No.
The conference is now in conversation mode. All participants are now unmuted.
Okay. Does anyone... Oh, we've got a question up there on the screen, Tom. More of a statement, actually. In recent times in Victoria, the experience is that some of our most productive burn seasons have been after drought years. It's possible that the autumn burn season may be delayed and run longer.
Yeah, so this is actually a fantastic example of the difference between, say, Tasmanian conditions and Victorian conditions, where I'm just not familiar with exactly what is ideal for operational burning in Victoria, and that's where the kind of regionality is really important, to get down and talk to people on the ground. What's important to you? How does that work? And then how does that interact with the climate conditions that we're going to see moving forward?
And I know Victoria are going to start investigating some historical records and look at how that impacts their prescribed burning windows will be impacted as well. Does anyone online have any questions for Tom? No, it sounds like you've covered off quite well there, Tom. No one's putting any questions forward. I'll just ask one up there online. What effect is, if any, is seen by looking at dew point temperature rather than relative humidity, which has temperature dependency?
That's a really good question, Mark. I think I might we haven't looked at that yet, but we could certainly include that in the current project, which I know you're aware of. For those that aren't, this was stage one of our prescribed burning work. We've got now some work in stage two. In that stage two, we're doing a lot more kind of development of sort of a prescribed burning index of sorts, I guess, to really sort of identify the interaction of all of these variables with each other. And yeah, using dew point, I think, Mark, would be a fantastic idea.
Thank you. Again, is there any questions for Tom? Okay. Well, I'd like to thank Tom for his time today, and if you do think of any questions in the future, you can direct them to me at the Centre of Excellence and I can pass them on to Tom. So once again, thank you, Tom, and thanks everyone for your time today.
Thanks, everybody, and feel free to contact us directly at Climate Futures if you have any questions about this. We're very happy to engage. Thanks very much.